in our last video, we talked about how we could get two possible products from a halohydrin formation. And I think comparing to the video before that, we had letterings for these two molecules. So I think we called this molecule molecule A, and this molecule down low molecule B. So we'll use that exact same kind of designation, molecule A and molecule B. And if you remember between from the video before that, we said that A was a major product and B was our minor product. So B is our minor and A is our major. And so then the question becomes why? Why is A the major product and B the minor product? And the rationale actually kind of goes back to this carbocation mechanism rationale. And so even though the bromonium ion mechanism is not a carbocation mechanism, it has certain characteristics of the carbocation mechanism. So because we have Br2 addition via bromonium, we actually don't get this kind of 1,2 hydride shift or rearrangement or anything like that. It doesn't really happen with bromonium, so it's very simple in that way. But what we can do is we can restructure the first part. So after we redraw the bromonium ion, and let us focus just on the bromonium ion for a moment. In this case, the second step is going to be the attack of that water onto one of the carbons of the bromonium, either carbon 1 or carbon 2. So it could potentially attack either one. And so what can happen really is when this mechanism is proceeding, you either have the water attack 1 or 2, but at the same time you can imagine two different scenarios. You can imagine that as the water is attacking either carbon 1 or carbon 2, you can have that bromine to either carbon 2 or carbon 1. Either one of those two bonds can begin to disintegrate. So let's examine what would happen if this bromine to carbon 2 bond began to fall apart. So if that began to happen, where that bromine to carbon 2 began to fall apart, what we'll have is the elongation and kind of disintegration of that bromine to carbon 2. So let's go ahead and take that bond, and I'm just going to kind of draw it as like a little bit of a dash. I'm trying to make it look like it's halfway broken. It's kind of elongating a little bit. And that carbon 1 to bromine bond, that's still, that's still there. And as this happens, you begin to get a partial positive on this carbon 2 as that bond begins to break. So as that bond begins to break, you get actually a partial positive on carbon 2. And so then let's compare and contrast what would happen if carbon 1 did the exact same thing, just in the opposite fashion. So if carbon 1 to bromine, if that bond began to break, we get something slightly different. And it would look kind of the same way as the top example, where that blue bond is kind of breaking apart, it's disintegrating, it's kind of going away. It's still kind of there, but not really. And then the bromine is still kind of hanging on just by a thread, and that carbon 2 to bromine bond is still there. Now that that 1 to bromine is breaking apart, you actually get a little bit of a charge buildup on that carbon 1. So that carbon 1 is losing a little bit of its electron, so it's getting a partial positive in this case. If you actually had this happening where you have a partial positive on 2 and a partial positive on 1, you could actually compare and contrast stabilities of these partial positives in the same way that you can compare and contrast full positives on carbons. And then if we were just comparing full positives, in this case we would have a secondary carbocation, versus in this case we would have a primary carbocation. So in this top example, it'd be kind of like a partial secondary, because this has 1, 2 groups attached, so this would be like a partial secondary carbocation, and the molecule on the bottom would be kind of a partial primary carbocation. And if you had to compare and contrast stabilities, the carbocation on the top would be more stable. And because the carbocation on the top is more stable, it's again this kind of rationale of drawing out an energy diagram. You draw this energy diagram out just like this. You could start on at this position right here, and you could follow this reaction diagram. It's going to go up kind of for a moment and then come back down, and this is going to be your partial secondary carbocation. And then if you went through the blue pathway energetically as the reaction proceeds, you would get kind of this scenario where it's a little bit harder to go up that hill to make your partial primary carbocation. So this is, again, on the x-axis is reaction progress. And so it's the same rationale as we've done in the previous examples when we talked about full positives on the carbon, where it's easier to go up this hill that's a little bit less intense than going up the more intense larger hill. And so the molecule is going to prefer to go down this purple pathway. And so once you go down this partial pathway, it's really going to be easier for the water to now attack this carbon 2 than carbon 1. And so now, because of that, we're going to be able to get our hydroxy attached to carbon 2 and not carbon 1 to a higher degree. So going back up here, we can see that carbon 2 held on to the hydroxy to a much higher degree than carbon 1 did. So it's just easier for that water to attack carbon 2 because of these partial positives. I actually was kind of telling a little bit of a lie before, whereas these two transition states, this partial secondary carbocation, it's actually not going to be located at this energy or local minimum. It's actually going to be located a little bit higher up. And this is going to be our partial primary carbocation. So because these transition states, you can never actually isolate them. That's the reason we have these energy maxima right here. So these would be the energy maxima, and this would kind of be an energy minima for an intermediate that you actually could isolate.